Okay, 1353, the trolley, has a couple of purchase components that we'll need to download. And so I'm going to go ahead into my my Windows Explorer, and we have Assignment 9. I'm going to go ahead with a new folder. Assignment 9, and this will be 1353. And so we have a folder to save the parts in when we identify them. Alright, so one of the things we'll need to do is see if these numbers correspond to a metric bearing. Right now, the number 99504 new departure ball bearing doesn't add up to anything or show anything, so we'll go do a search for ball bearings. And then looking down through the list, we have to decide, well, it's a trolley, it might have some wear. Probably don't want an open bearing. Shielded wouldn't be bad. And then sealed is probably one of the better. So if we scroll down through here, so I'm still kind of looking for that 99. Nice thing about sealed, they're pre-lubricated. They pretty much don't require any maintenance. So we're going to pull up the calculator, and so 0.5512 divided by 0.03937 equals 14.0005 millimeters. So fly that out of the way. We go and we find a 14 millimeter. So 35 millimeters and 62. And I'm going to click on the part number, go to its detail. Right, and then we need to verify it against our numbers. So float that a little bit that way, and just off screen I will clear. And we're 1.8504. So might as well call it 5032. Let's see if we split that, that's 5,000. So anyway, 0.03937 is our number, and that is 47 millimeters on the OD. So that doesn't bode well. So there is a 47 millimeter, 14 millimeter width. Alright, so it went down too far, so that's looking better. And then the shaft diameter of 787 to 74. Alright, so 787. And if we go back to conversions from 2 millimeters, we're going to be really close to 20 millimeters. 0.03937, 19.998. So it kind of depends on which side we round it up to. So 20 millimeters ought to be pretty close. If we need to update the shaft to 20 millimeters, then we'll see if it fits within the tolerance zone, the 781. Well, we got a little bit of running fit there. So all right, so I'm gonna fly that out of the way. Well, let's see. So that takes care of the bearing. So 47 millimeters, 20 millimeter shaft. The file product detail, and then we're going to save this. And was that a sealed? Seal type was open. And before I get away from that one, see if there's also 47, okay, for shielded, and 47 millimeter by 12 millimeter. No, there we go, 47 millimeter by 20 millimeter. All right, for the shielded. All right, and then we will save that file. That's going to go to my downloads. And then I'm going to jump back over to the Windows Explorer and just put that in my project folder. This was something that we're going to use regularly or had for sizing. Then I might create a folder in the design library for these components. Right, so the other item that we need then is a couple of axle, we have snap rings. And so I do want to check the design library. O-rings, power transmission, internal. So snap rings that they're showing don't have the E-clips, the retaining, the holes to help put them in and take them back out. So I think we'll find something comparable and then go in for the fit. All right, so since we have a basic ANSI, the 656 would probably be clearance for, well, let's double check, because that one's, if that's an external, and depends on which part of the shaft. So, all right, so that one is on the external. And that goes through. Oh, went too far, so, okay, so on the bearing, and that comes out. All right, and the side view, we're looking at the stack up, so it's retaining through the shaft. The shaft comes up to bearing on the shoulder. Oh, and then the outer. So where is the second retaining ring? So, oh, they're on the internal for the to hold the bearing, and then that holds it up against the face. And then the keeper plate slides up into the slot. All right, kind of getting that. All right, and then the side 7/8, and they're wanting to put a cotter pin. So I'm not sure where that one's going. Maybe through the base. Said to ignore items 7 through 14 on the list. We're going to read through those real quick. Slotted hex nut. Oh, so they're going to do a retaining. Oh, okay. So it's 8 1/4 inches long. It goes all the way through the base, and then is getting a castle, basically a castle nut or a slotted on the back side, plane washer, and a cotter pin, and then the machine screws to retain. So, all right, so that's looking doable. So we have an internal, couple of internal snap rings, and a couple of, and then one external. All right, so let's go ahead and kind of identify the hardware. I don't think I need to download the snap rings. So we're going to start. Let's go ahead and start with the axle, and we'll get this going. All right, so the axle, pretty straightforward. Couple of grooves. Says that we'll be doing a revolve. The back side of the bearing is going to contact that radius. So I don't know if they're looking to seat that or give it some clearance. So front plane, sketch. We'll go with our center line, infinite length, horizontal infinite length. And then L on the keyboard puts me back into the line. I was going to look at the chamfer on the outside. And we'll just do this first part to get it kind of established. Alright, so I don't really have to put in the chamfer. It's calling out for grind. Okay, so 0.062. And I'm going to say, I'm going to shrink that a little bit. Alright, so maximum material condition, 1.178 to 1.175. Oh, okay, so 1178. Too many ones there. Alright, 1.1178. So that should be right at 30 millimeters if we change this over to metric. And so maybe that'll be the task for this is since the geometry and the parts are basically duplicates, one of the things we may go back and do is optimize for metric since these are pretty close to our numbers anyway, and see what we get. All right, so the inside 0.875. And we have 0.141 and cancel because I did not get out of the dimetral. So escape 141. And from the edge, ignoring the chamfer, 0.875. And we'll set, oh, not equal. Control Z, we want collinear. There we go. Alright. Alright, and another chamfer. Since I'm including them in the sketches, we'll go ahead with that. And don't know if there's going to be a little bit of a flat there or not. We'll see if that plays out. Alright, so 0.06. I'm not sure what that grabbed. Might have been the midpoint. Alright, so 45 degrees. L on the keyboard, get back in line. I think I'll put that radius in last. Alright, the other snap ring groove or retaining ring groove. And then another chamfer, and then back. And so in the previous example, I didn't close it off, and it asked me to, when I completed the revolve, if I wanted to close it off. So we just make it a habit, it's a little easier. 2.875. Okay, so not entirely unexpected that it would do that. So we can pull these back in pieces and kind of rearrange as we go, as long as it doesn't get too crazy. Alright, so based on the way that moved, we're going to do select, control select, and collinear. The geometry then, the 656 to 658. So 0.658. And then the outside was the 7871. 0.7871. Alright, same thing. Oh, we're on the center line, so go ahead and bring this out. 0.06. And either picked up a parallel or a perpendicular to something. Alright, and then the maximum material 100 to 104, so we'll go with the 0.1. And then the distance is 0.556 to 553. So 0.556. Alright, so let's see what's able to move and why. Alright, so overall, then the dimension that I'm missing is the 0.843. Okay, so that gets it fully defined. So the radius of 0.03 and features revolve. Alright, so coming back into the edge, internal face, we'll go for 0.03, and then we're ready to save. Alright, so this is item 4, the axle. Alright, the keeper should be fairly straightforward, so 1.75, 1.25, which is clearance for the 1032s. Okay, so that'll be a sketch on the front plane. And we want to take advantage of that symmetry, so just a rectangle out in space, hold down the control button, we'll go to the midpoint, width is 1.75. Since there isn't any additional geometry, we'll do this in one sketch. And if we go line and for construction, then we can use the symmetry. Let's see, sketch tools, I don't often, selection, nope, sketch entities. Alright, so we can find a circle down in there. I don't often use that one, just wanted to point it out. And we're going to mirror those over. And 5/16 from the edge, 312. And 0.25 or 1.25 on center, and 7/32. Okay, so 1.25, and we got an extra couple of digits in there, so we'll just overwrite 218, and then our thickness, 1/8 of an inch. And features extrude 0.125. So this is item 6, the keeper plate. All right. Next item then. So let's see, 2.25, 4.5. We have the item 3, the crosshead, and it is through. All right, so file new, part edge. Let's go into the top plane and kind of looking towards the assembly. I would really like this to be at the center. See if it'll let me change it. Oh, yeah, let me change it, but I lost my point, so we'll drag that back. Corners and midpoints, kind of a personal preference. So we'll go 4.5 and then 5.125. And then I'll extrude that out to a distance of 1.75. Okay, and then the through holes, those can't really see those becoming, well, I'm going to say the through holes, we maybe could change those over to threaded holes, and it wouldn't necessarily have to go all the way through the 5.125. So in that case, if there's a possibility, we're going to do the hole wizard. And 906 should be just above 7/8. So all drill sizes, let's show the decimal values. And then 906, 29, 30 seconds. And then the end condition is up to next. Go back to the positions. And I want to use the symmetry, so we'll go with line and for construction. And select Control Select for the mirror of the entities. And we're given a positional between the two, 2375 to 2372. So in this case, we have a 3/1000 variation, and I want to say that for position, we should be considering a mean value, so 735, and then we'll see how it plays out with our tolerance. Alright, so this is going to be a limit dimension plus or minus 1.5 thou. And then the decimals, we'll go ahead and put it at 4 decimal places. So I was looking for 372 and still had one too many zeros. So tab, let it update. Alright, so 372, 375, mean value for the position. Alright, so y is 875, so if I were to find the midpoint of the center line and then come back and make one of those horizontal, that will position, and then we accept. Alright, so let's see what we get. So 0.75, if that's going to be for a hex, we'll see how close we're able to get with a standard counter bore. So a binding head screw, probably a standard hex bolt. Know that there were a couple of hex bolts called out. I didn't see a 1 required, so whatever this is mounting to. And then we'll go up to the 7/8. Fit for, what is 0.75? Oh, now if it was 0.7, diameter 0.75. So that being the case, then 3/4 inch. And let's see what it looks like normal, show the custom sizing. So we're at 781. It makes me think it's going to be a 5/8 11 again, so let's go down to a 5/8. And then we're at 0.65 and loose 0.6719. Depth-wise, we're pretty darn close. Alright, so in this case, we're going to make an adjustment. Just be aware that when you override these values, that you're responsible for making sure that the fastener is up to the standard. All right, and then position is at the center of the block, conveniently enough. Place it and accept it. All right, so ready to save, and then this was item 3, the crosshead. All right. Looking at the Item 5, the adjusting shim. Very similar to the keeper plate. So rather than redraw all of that geometry, I'm going to open up the keeper plate. And then we're going to do a file save as. And I want to save as, copy, and open. And because I haven't put this in an assembly, there aren't any issues with the naming being attached to the assembly. So 5 becomes the adjusting shim. Okay, and then up here we'll make sure item 5 adjusting shim. Alright, so if I go back into the dimensions and we go up to 4.5 on the length, 2.375 on the centers. And why didn't that update? Didn't give it enough time. 4.5. And then the height is 1.75. Alright, so in this case, I'm going to go ahead and put in the 0.875 rather than tying it to the center line. Hole size is 15/16, 0.937. And then we go to rebuild. That makes this the larger plate. And then it is also 125. So we go ahead and save it. And then we have that piece in the mix. Alright, so the tumble to remove burrs, hot rolled steel, so a 1018 10 series. And then tumble to remove burrs. Well, we'll just remove the burrs. Okay, so then close that one up. We're going to the side plate then. And then that one is still open, so file new. Hard inch. And we'll sketch on the front plane. And we still have symmetry. So pretty much the same as what we built. So I'm thinking with a corner rectangle, since the base kind of has that initial step up, we'll do the midpoint. It's 4.5 wide. The first step is 1.875. And to switch that to construction geometry, so when it comes up. Alright, I'm going to go to center line from the pull down or do line and change it, so that becomes vertical. The overall height then is 9.25. And the width at the top, 1.875. Alright, and then we have the holes. So again, maximum material condition is 1.116. And from the base, now we need the other 2 holes. So that's going to be 1 inch. Did not click to complete. Alright, so we will set those to the mirror. And those were, well, they weren't called out 3 times. Oh, there we go. 2 times 0.875. And they are 1 inch from the base. So, considering the others were 875, that gives us a little bit of a gap. And then the distance is going to be the same as the block, and since that was the tight tolerance, 2.3735. Bilateral dimension, 0.0015. Boy, I sure like that third zero. Okay, half a thou, no. And this time I'll just copy it, since I'm having so much fun with those zeros. And then we're going to go to 4 decimal places. I don't think for the drawing then, oh, so I left that as bilateral. I want to go limit. There we go. And then we can double check. And I don't think I did this one on the other one. We can mark for drawing. That one in place. And then in relation, between the holes is 7 inches. Okay, so we have the 1032s for the plate. We're going to extrude this out, and it has a depth of 0.75. And then S key, hole wizard, tapped hole. Reset the custom sizing to what we're doing currently. And then we're going to go to a number 1032, 1024. And up to next. So positions. So we'll stay with the center line. I would just as soon use the mirror and the symmetry than do the stack up of dimensions where there's a possibility of making a mistake. So 1.25. And then from the hole center to the point, 1 inch. And we'll go ahead and accept. And then we're going to do save. Is number 2, the side plate. Alright. So then that's going to leave the trolley wheel. Just a quick double check of my numbers. So not geometry. Alright, so 1/2 inch core, 3 holes equally spaced. Alright, and then we're looking at this profile, so that's going to have some complexity. We're not concerned with the holes, but the retaining rings. And we've already sketched in for those, so I think I'm going to try those with the retaining ring tool, just to illustrate that. So I'll fly out the number 1 trolley wheel. All right. And then on the top plane, looking at that profile, go with the center line, vertical, infinite length, onto the origin. Don't really care which side of the hub is going to be for the geometry, so I'll start sketching this out, apply that back in. So I've got kind of this segment. We're going to do the retaining rings with the groove tool. So that comes out. Saw that there was, okay, the profile 375 on the height. So we can make those two items collinear and then come back and make them equal. And we'll go 0.375 and 0.375. Okay, for the diameter, all right, maximum material condition for our first number, we have the 8504 and the 18498. So 1.8498. Smaller number is my maximum material condition. For the step, so first number out of the way, and then 2-inch 204 to 2-inch 004 is the groove. All right, so that'll come up here in a little bit. 2.5 to the hub, that's the one I'm looking for. So the outside, $2.5. All right, and then we're going to need some more geometry. So the wheel falling away, we're going to put the radiuses in at the last. And that doesn't look too bad. We'll be able to go all the way around. Alright, so the very far outside, 7 1/8. And then to the inside step, 6.375. Nope, that's to the outside of the wheel. Alright, and the next one in, 5.25. Alright, those should be on the same plane, and then we can start working with some collinear. And then we can start working with the heights. Alright, so the overall height, 1.812. So 1 13/16. Alright, so it inverted itself a little bit. We're going to pull that back. Let's see what we have for a step. If that comes up even on the face, no, it's telling me that we have about 1/8 of an inch difference. Okay, so let's fly. So let's make sure where I saw that. So the outside edge, 1/8 of an inch, and then that goes to the hub. Okay, so kind of a small amount, 125. All right, and then the outside step, 0.437, 7/16. All right, and then there's a radius, 0.562, so let's go ahead and put it in as a fillet. On the interior edge. All right, so the rest are going to be pretty much consistent, so those, now they gave it a 15 degree. So let's see where that is coming off of. So if that comes off tangent to the arc, well, then I'm going to need the arc. And looks like it's coming off of that tangency point. Well, let's see what that does to the dimension. Alright, so let's get out of the fillet, and then I'm going to take the vertical off. Alright, because it has that, basically that parallel dimension, I'm not going to be able to use that. And those can't be collinear. Alright, so let's get the dimension back in before we start making adjustments for that 15 degree. Alright, so starting point, And let's see, that interior radius was 0.18. Okay. And we're not given the dimension to the center of the radius. So the 15 just kind of back a little bit. And then since that dimension pulls, thinking it's going to be at the radius, so we'll make it coincident. And then 15 degrees off of my vertical, so might as well go back to the center line. Alright, so that kind of jumped out there a little bit, but that gives me the geometry. Let's see, with the wheels, sometimes we're looking at the crown. It keeps expanding out on me, so there we go. No crown. 9.5 degrees coming back to the face. All right, so that's interesting. So 6.375, and that looks like at the bottom of the radius. So those were 1.25s. All right, so that one we take the vertical off of. And there again, the dimension is driving it, so we have to take that one off. All right, I'm going to put the fillet in at 0.125. So I'm not exactly fond of the way that these are dimensioned, but can't do a whole lot about it. All right, so 9.5 degrees from. Need to pull that just a little bit off so we get the angle started. Now we'll be able to pick that that outside edge and the line, and that'll give us the 9.5 degrees. All right, so near as I can tell, 6.375 is out here, and it's at the bottom of the radius, and then the radius blends up and in. So that being the case, move that out of the way, find our dimension, and bring it in. Oh, and I put a 0.5, I guess so, 9.5. Got an extra 0 in there. Alright, so that's quite a bit different. It's kind of hard to tell what's going on in the with that in the angle. Oh, and then they got me for another 8 degrees coming off of that angle. So back to that point for the 0.437. Wow. So that being the case, take the 0.437 out. We're going to take the horizontal off. Right, so identifying these geometries. Right, so that's letting it go. The 0.437 is to the bottom of the radius. Again, that's from the visual. And then we have the non-parallel lines, so we can go to 8 degrees. And all of a sudden this became a little more complicated. Alright, so we'll fly this in one more time and see if I missed any more dimensions. So overall, 437 intersecting at the radius. And then 9.5 degrees, 8 degrees off of the back. Radius of 1/8 of an inch. 1/8. 15 degrees on the interior. Alright, I think I got them. Alright, so interesting trolley wheel. Let's go ahead and revolve. Alright, so it ended up exactly like like the drawing, but that's okay. We have good geometry. I'm not going to worry about changing it. All right, so opening up a sketch on the inside face. Let's go ahead and generate the base circle. So 4-inch base circle for construction. Pick a quadrant and dimension of 0.5. I'm going to set that one to vertical. No, I should have put the 4-inch in. Okay, so now we can go into our circular pattern. And we're going to have 3. Alright, so once again, I'm looking for the point. Nope, it did something there. I know it's there. Alright, so if this was a whole wizard item, that would be counted in the instances. Since I was able to drag it back to the origin and get it to go fully defined, I'm inclined to leave it. And we'll extrude cut and tell it to go up to next. Alright, so we have enough into this one. Well, we have way more than enough into this one to save it. And we'll set the trolley wheel. Alright, so I'm not ready for the rest of the fillets just yet. So we have the inside geometry. And if we go to, let's see, right-clicking and going to the SolidWorks add-ins. I want to say that I saw it, but then I'm not sure where I saw it. So I may have to go back to the standby. So there is the SolidWorks toolbox, and that is all of the fasteners. There's also under tools. Alright, so a little bit different than a little bit different than 2017. So I'm not seeing it up there. So I'm going to go the other way and go into the add-ins. Give it a second to catch up. Alright, so we have the SolidWorks Toolbox library is active. I want the Toolbox utilities. And while it's loading, then what the utilities are going to do is give me retaining rings, O-ring grooves, we have a cam calculator, a beam calculator. There's some different geometries that it will create. Okay, if it's not crashing me right now. Come on, you can do it. Okay, it was just waiting for me to pause the video. So, tools, toolbox where we went before. Now you have the structural steels, which are the I-beams, the grooves, the cams, beam calculator, and bearing calculator, life expectancy for the bearing. So groove, we're going to pick up for the retaining ring. And we'll give it a chance to catch up. Well, we'll let it pause while it's catching up. Okay, so O-ring grooves and retaining ring grooves. So this is an anti-inch. It is a internal ring. And actually, seeing how we're pretty close to the metric sizes, and we're going to switch to metric anyway, I'm going to do a basic internal. And then we're looking for that, what did we end up with? 2-inch. So actually it probably should be pretty close to a 50 millimeter. Alright, so we'll see what that gives me. The groove diameter, selected diameter. Alright, so I have the inside face selected. I had the inside face selected. And it jumped over to 47 as a default. So 49.8, that looks pretty close. And we'll go ahead and create it. And we can always make adjustments to the sketch once we determine how close we are. So done. And then the groove, expand it out. We're going to edit the sketch. Alright, so we still need center line. For this, we're not going to need it to be infinite length, so we just need to do the revolve cut. Alright, so the width that we're given is 0.125. And so that was quite a bit smaller. Alright, so we're probably going to have to dissolve this sketch because I don't know that those numbers are going to line up. So pretty close. So maximum material would be the 2-inch. The depth is going to be to the wall. Right, so I can just drag that over. And we didn't get, let's make sure we get some verticals in there. Vertical, horizontal, horizontal. Alright. So I'm going to go ahead with the second center line. Well, let's put it back in shaded with edges. And we'll just come out some distance. I need to grab my geometry and then control select. I'm going to mirror that over. Alright, so that's going to give me the depths. Now, once again, we're on the interior, so this was 553 to 556. That falls into the category of the positional again. Our bearing is 551, so that's a consideration that we have a couple of thousandths of clearance for the bearing to sit in there. Alright, so I'm just kind of clean up on that, and then we have an 1/8 inch off the wall, so we'll jump back into the hidden lines removed. And then the lower edge, okay, back to, okay, control 5 didn't work, control 6. Alright, so just kind of verifying that on the step we're up, over, and back. And we'll zoom up on that. So 0.125. what was the groove size? So, nope, groove size actually was a little bit bigger, 160 to 158. So, oops, we can catch up to that, 158. And then our dimension is still 553. All right, so that looks pretty good. We can go ahead and accept. And that gives us the groove. But I'm not sure that that specification is what we need it to be. All right, so it's still showing me an underdefined condition. I'm getting all kinds of fun stuff there with the view. All right, make sure I know what I'm picking, get back into the shaded with edges. All right, so that all looks pretty good. So if I right click, just wanted to check on the groove description. All right, so let's pick that up. The 069, so 1.75, yeah, that would be about 1.75 on the groove width for the millimeters. All right, so we have it in there. And then let's go ahead and save. And our radiuses are 1/8 of an inch on the outside. Looks like a sharp edge on the corner. The interiors, don't really see anything. Well, we have the 0.18, so that would be probably typical. And 0.625 on the outside. So we got a little bit of everything there. So let's start with 0.125 and accept it. And then the outside of the wheel is the sharp. Okay, and we already built the 0.18 into the inside to get the angles. Okay, so that's looking pretty good. Let's see, it looks like we missed one there. So that was the inside, the outside. Alright. And then we'll go one more. 0.06. Alright, so let's take a look at what it does in section. And would really rather have the top plane. Well, let's go to the top plane. And rotate over and see if we can get pretty close and compare geometry. Alright, so my core, half-inch core hole doesn't intersect through that plane, but the rest of the geometry looks pretty close. Not seeing anything terribly missing, so we will call that one good. Alright, so clicking on that. Let's go back into the sketch 4 just real quick since it's still got the minus sign. Would like to see. Put a center line up here for me. And not sure why that groove or why that origin is so far out. I ended up drawing one, and I don't really want to delete that one. Well, let's see what happens if I delete it. Alright, so everything was tied back to the original, so, okay. If, so maybe that wasn't a good thing. Alright, so let's see if we can undo it. Alright, so their center line geometry is the one they want to keep. So I'm just going to connect it. And I saw that briefly flash up. Alright, so it's still underdefined. And make sure it goes vertical. And now we have a fully defined sketch. So most of the time the center lines won't affect it, but in this case it did. Alright, so we'll save. Good. Alright, so here's where it gets interesting. We drew in inches. We made the one adjustment for the ring. And if I switch over to millimeters, grams, and seconds, then when we go back into that sketch, we're going to see everything in millimeters. So 11 millimeters, pretty close, 46.025. So 46, 180. Don't know that I would go down to 4, but we could call it 4.5 millimeters. I think that would be okay. All right, so making the conversion, jumping over to millimeters, we're going to lose a little bit and gain a little bit on some of the numbers. All right, the ones that I don't want to mess with, this internal, right, because that was the 447, and then the 63.5, we can leave those. All right, staying with the 3/8. Well, that could go up to, if we thin out the web, no, I think we just need to leave those two alone. And then I don't want to shift the position there. I think we're okay. So we're just going to make a few decisions on the overall. So 181. And that's the basic. When you see the instructions to convert to metric, that's pretty much all we're trying to do is what makes sense to, if I see 4 decimal places or 3 decimal places on a metric number, do I really need those? So let's go ahead and save. I think that's the components. So we'll set for the new assembly. And I'm going to browse to the to item 3 will be the first item in. And again, accepting it because it is in position. I don't have to flip the orientation, just going to the check mark puts it origin to origin. Advantages and disadvantages of our metric to inch conversion, and I only did one part. We can certainly go through the rest. And the question is, do I want to bring in individual components or have the mirror, since this is going to be a pretty decent sized stack up. So for this one, we'll do a mirror, and then we'll see if there's any issues with setting it up that way. All right, so not the keeper plate. We want the adjusting Shem. Yep. And what I'm going to do with the adjusting Shem is we looked at a reference, mate reference. So what this is going to allow me to do is set an edge, and it's going to be default mate, any orientation. And when I save this, I can go back into the assembly. Since it's open, I will insert components, and I'll grab the adjusting Shem, and now whatever cylinder that I hover over, it's going to try and make it concentric. Right, it also made the edge coincident. Right, so that little bit of mate reference is going to let me be a little more efficient dragging it in and getting it set up. And then we can go concentric. All right, so apparently on my numbers, add this mate and break. And then there are misaligned options, which it's interesting that came up. So if we use the misalignment options, it's going to allow it to stay in place even though we're probably not more than a half thou off. But notice that the concentric picks up that extra symbol. So I would be interested to know why. So 2.37, let's go ahead and adjust the units and take it out where that specific case it was 4 decimal places. Alright, so 2.3735. .375. Alright, so since those weren't as critical, it was position, and the hole is enough larger that positionally it will float into place. So that's where the misalignment's coming in. Alright, so if I'd gone to 2.375, then the plates, the outside piece, yeah, really it's the side plate that has the same dimension. So positionally 906. So I don't think really the 3/1000ths. That holds it a little tighter than a nominal dimension, but I think probably just leaving it to the 2.375 will line all those up, because an 875 hex head bolt, so a 7/8 bolt going through there, is going to be fairly tight through the outside, pretty well loose on the adjusting shim, and then a little tighter but fairly loose on the through. So that stack up is probably something that needs to be re-examined. But we'll leave it off alignment or misaligned, and then we're going to insert for the side plate. All right, and didn't set a mate reference for this, so we're going to bring it up coincident. And then because these numbers, move it a little bit closer, these numbers should line up with the tolerances. Then I'll have concentric. And one of the reasons that I do concentric to concentric is exactly for that reason. If there is a misalignment, if there's something that doesn't stack up, then it's going to bark at. And I want to say it was 2017 when they added the misalignment, allowing it to go ahead without having to go back and correct it. Alright, so insert. I'm going to bring in our first item. Was the item for the axle. And then we can go back and look at the keeper plate. Alright, so same thing, we'll line that up. Go in concentric. Alright, in the face. Alright, and I also realize that I'm cruising through these mates fairly quick. At this point, you should be getting used to the mates and the coincidence. And I want you to be able to see something that is closer to real time. Right? That you can expect that once we get into the rhythm and the workflow of these projects, that it will go a little quicker. All right, so I'm staying insert component. We'll bring in the keeper plate. All right, same thing. I didn't set a mate reference. If I had, it would be even a little faster, so coincident. Since I can see this geometry, we're going to go in. I'm still trying to go face to face, so get used to zooming in. And concentric. Alright, and then if there's a misalignment, I want to be able to pick it up, so concentric. Also, positionally, for this to act as the keeper, there should be a little bit of clearance. Right now it's showing interference. Maybe. That would be an interesting one to look at, to see if it is actually touching or if there's enough positional that can sit a little lower and we can still get the screws in. All right, we're ready for the bearing. All right, I'm going to browse over to and pick up the bearing. One of the things with McMaster cars, very often they come in with sketches showing. So more than I needed. All right, so we'll go with the shaft, and then to the, well, I say that I would like to see where it lines up with the edge, and then sitting on that radius, if that radius is a clearance. So yeah, kind of. Seems like there'd be just a little bit of float in there. So I'm going to bring it up to the edge. Alright, so face-to-face coincident. And that looks like it's in contact. So I don't know about that 30-second radius that we left in the axle. It seems like that's going to bind up, or it's going to offset it enough that it's going to be sitting on the retaining ring. Alright, so we'll figure those out. You may want to pull that back a little bit once I get the ring in. Alright, and then insert component. We're going to bring in the trolley wheel. It needs to flip around, so a couple of rotations on the Y. If you're not, we haven't really needed it in this one, but the interface allows for that rotation. Alright, so those two faces are going to be concentric. Thinking that face. And we'll rotate around and I'll find the inside wheel face. And those will be coincident. So even though that was supposed to be 14, oh, I picked the wrong one. So let's Control Z. And Control Z again. Alright, so that puts it back out here to where that face and that face are coincident. Oh, I got rid of my concentricity and all those undos. Alright, didn't take something there, so let's go check the mates and make sure. Nope, not yet. Alright, so got a few lines for it to calculate, a few circles. Alright, so making sure the face is selected. I tried to pick a little too close, so here we have the concentricity. Alright, and then as far as rotation, I think it's okay that that's able to rotate. So let's take a look at the hardware that we're going to need. We'll do the retaining rings first. So we're going to have an external and then two internal. So going into the design library. Oh, I got the file explorer. Let's go to the design library. Okay, so previously we had navigated over to the toolbox, ANSI inch, found the retaining rings. We need an external ring first. And so do we want the clip? Let's see, so a C type, and then the E type, or the, would that be just the one? I kind of prefer the ones with the holes in it anyway, so I'm going to place it. Let's see, it got a little bit bigger there. I think that one looks pretty good. And the shaft diameter picked up 21.4 millimeters. So even though we're in inch seconds, did I pull a metric clip? Groove diameter. Alright, well we can always adjust it later. That does look a little on the large size though. And no, I don't, 0.658, that's not even, okay, so 16.7. So right clicking on that, I can edit the toolbox component. Oh, well, we got all of them then. Let's see, so would think that, no, that looks like it's going to be a little too tight, the 11/16. Groove diameter 646 and reference 046. Alright, so let's do a Control 8 on the in face. You can hide a bunch of those that we don't need. So I'm just going to go through and tab, and that looks pretty good. So no, that's not quite it. And went right up against the edge. I think I need to reverse that geometry anyway. Alright, so trying to rotate in to where I can get a measurement off of that edge. Alright, so 16.7. So if that's the case, then the 17 millimeters should work pretty good. So let's see, is that the OD? Yeah, no, the groove diameter. Alright, where that one's still pretty big. 3/4 actually looks pretty good. So let's go ahead and accept that one, and we'll get a measurement off of the ring side. So if I pull it out a little bit, then the ID, yeah, I'm just going to switch back to inch, pounds, and seconds. Alright, so radius of 352, and we were 6.5, so no, those still don't quite add up. Alright, so the toolbox group, I think the, come back to that, that diameter, the 658, 656. They held that pretty close on tolerance. 6.3, but that's going to be really embedded, so let's stay with 11/16 then. Alright, so I want to make sure that that doesn't move. Let's check the mates. So we have concentric, and then coincident to the face. So yeah, I think that looks pretty good. Alright, and then I'm going to tab to hide the bearing. Alright, so just a little bit of geometry in that one, and we have enough float there to, so standard E-ring, so that snap ring that they picked is probably a little on the large side. So we would want to come back and verify that, that dimension. And updating to what is available off the shelf. And then if I hold the Shift tab, then the external will come back. Going to switch, go back into the design library. And now we're going to go to internal. And drag out. Okay, well, maybe we should do the first, no, the nearest groove first. Alright, so 1 11/16. We know that that was a 2-inch groove though, so, or a 2-inch OD. So groove diameter 2.12, so that's the compression size. 2.056, I think that would work a little bit better. We know we're going to have to compress it some. Alright, so we'll go ahead with that one. And then set it for, did it not apply the second one? It's still asking me for it. I think I see it, it's just, it didn't, it lined up to something, just not sure what it lined up to. Okay, so we're going to find that diameter, go with that one, see if we can make those concentric. Alright, so we got the retaining rings in there. Alright, so I think that that's probably a good fit. We'd go back to the manufacturer and see what the recommended diameters are and update those, update that model to those values. Alright, so Shift tab. Nope. So let's expand out. And where is my flyout? Okay, so there's the carrot. We're going to show everything again. Okay, so that looks pretty good on that end. Let's see, before I mirror this, we're going to have a stack up down here, but those are going to be pretty much the same. So they're calling out for a round head machine screw. And well, we're using hexes, so I don't know that it's going to be that big of a deal. We'll find the bolts and screws. Pick pick whatever you're familiar with. So there's a round head, and we drag it out, and it finds the 1228 because that's the hole we lined up to. We're going to go to 1024. It has to go through the 1/8 inch plate. Doesn't really need to go all the way through the 3/4 inch plate though, so we can go up to 1/2 inch. I think would be plenty. We accept. It says we're ready to add the next next screw, and then I can go ahead and accept it. Alright, so at this point I'm going to save and rebuild the document. Alright, so the 7/8 by 8 1/4 inch. Hopefully we can find one of those. Alright, so it is a hex, And the description, 875 by 825. So now we're going to go to a hex head. I think it's, well, we'll start with a standard. It will probably end up being a heavy, maybe even a hex finish. See what size we can go up to. So 7/8 14. It would be a fine thread, probably the 7/8 9. That looks okay. I would stay with the coarse because we're doing the castle nut. Oh, I guess it would help to make those just a little bit longer. Alright, so since I missed, I'm going to highlight both of them, see if it'll adjust them at the same time. Length of 875 is not quite getting it there. So scrolling down, we have 8 and we have 8.5. So considering that we still have the other half to put in there, we're not too far off. Also, I did not include the washer in the stack up. All right, so I'm going to back out of this. Control Z, and we're going to take a look at Smart Fasteners. So Smart Fasteners is a way of doing stack ups. It has some advantages, but it also has traditionally come with a few headaches. And we're going to go for those two. And it found a tapped, oh, that was the body. All right, so we want to add to the feature. All right, and the group. No, that wasn't the group that I wanted. All right, so Smart Fasteners, yeah, don't show again. All right, so edit the grouping. Drag a series in to another group to combine it, or drag holes from one series to group to split the two. All right, it's supposed to be recognizing those. It's finding the 1024s, but and usually populate all is about the easiest. So that should be the body name as the last feature added. Yeah, 1024. Just going to trace that real quick. Yeah, so that's where the body name's coming from. Alright, so we'll go ahead and add it. And the group, now it's still finding that one, so that one's not the one that I want. Alright, so I hadn't added that one. Alright, I thought I was going to do Smart Fasteners. It is not cooperating the way I expected it to. So socket head cap screw. It's trying to put that one on top of that. Alright, it's not recognizing the larger hole, so maybe since it's not threaded, let's go with the block just to double check it before I go to the other route. And still thinks it's a really big socket head cap screw, so I found the 7/8 14, which is closer. That's still not quite what I'm going for. Alright, so given that that stack up's not cooperating, let's go back and find the washer. We need to put one of those in first. Alright, so I kind of mentioned that the Smart Fastener can be a headache. If it populates all, it usually does a pretty good job. Since I already have the couple of the screws in there, that may be what's holding it up. So plain washer A. We'll just go with the preferred narrow. Up to a 7/8. That one looks pretty good. Alright, and then actually I think we're at the point where to make this work I need to go ahead and mirror everything. So pretty much everything except for the crosshead we can select, and for the pattern then we're going to mirror those components. It needs a mirror plane, so that should be the front based on orientation. Alright, scroll down, pretty much has everything, so, and I did not do the second, so let's go to the next and view the orientation. Everything looks okay. There are sometimes other solutions. Alright, so in this case it's pretty straightforward. Everything on this side's on that side, but if we look at some of the different 204, not quite sure what it's trying to, if it's inverting anything there. So we just want to be aware of that. Mirror type is bounding box, and then center of mass. Don't need an opposite hand version, it's symmetrical already. Alright, so I think we're okay with that. Alright, and then now we can put in for the hex head. And that'll go to the washer. And it is a 7/8, we said 7/8 9. Alright, it can have a length of, we went to 8.5 inches. Alright, so that's going to be a little bit long. Thread length of 1.5 is plenty. It doesn't need to be threaded all the way through. Go ahead and OK it, and then come back. Alright, so we'll see if the if we can find a castle nut. Alright, so the hex slotted nuts, heavy hex slotted. So we're going to add it. It is a little bit long, but I would rather have that that extra than, but it is going to adjust the node of where we're going to put the keyway for the cotter pin. And then I believe if we really wanted to take it that far, that there is a clevis pin, dowel pin, straight pin. I think we can find, actually could find a cotter pin and put that in. All right, so to fully take this over to metric, we would go through each of the parts and update the values, making decisions on tolerances. The piece. At this point, I would like you to at least do the trolley. For organization, then, I'm going to grab all of the fasteners, and we're going to add to new folder, which is just off screen on the bottom. So fasteners, and technically it would be 2 because the mirror component pulls up the folders. Alright, if we added material to each of these, so the crosshead block was hot rolled steel, so pretty much a 1018. Let's see what we have available. So 1015 cold drawn, 1010, Alright, so we'll go with the 1010 as a hot rolled bar. The side plate also is hot rolled. And then, let's see, well, if we go in order, the adjusting Shem, is going to stay with the hot rolled. So if I'm applying these a lot, we're going to need to add these to the favorites, since we're just going down through. Okay, and then the axle. Axle was a cold rolled steel, so we can do that as 1020. Right, so basically for a weight calculation, we're just going to apply a bunch of steel to this and trying to keep it as close as possible. But we want to pay attention to the materials. And so the keeper plate was also cold rolled. And then the ball bearing, that's probably going to be fairly negligible in weight. We're talking compared to the body and to the wheels. And then C1 is usually a plain carbon, so if it isn't, it is now. And material, we'll just apply the plain carbon steel. Alright, the bolts, yeah, those are going to have a little mass to them. But let's go ahead and see what we get at this point. I'm going to go ahead and save, rebuild, and then under the evaluate, we'll go into mass properties. And so this one is 37 pounds. So at least with the locating roller for previous 270, we're not quite as heavy as that one. But there are certainly places that we could save some weight and probably not sacrifice too much on the structure. All right, so there's some other things that we could do to this. This builds it out to a point that we can get some good information, go through, make some decisions on currently available materials and off-the-shelf products for the assembly. All right, we're going to call that one good.